Hey guys, welcome back. It's time for chapter 11. Now we're talking about angular momentum, and finally we get to our third fundamental principle, and that is the angular momentum principle. So let's do it. I want to begin by describing a situation in which a child runs toward a merry-go-round and hops on the merry-go-round, and the merry-go-round spins. What we discover is that for a given velocity and a given mass, if he runs in such a way that he hops on at the rim of the merry-go-round, it spins fast in the clockwise direction. But if he jumps on a little bit closer to the center, then I should say if the perpendicular distance between his line of motion, his trajectory, and the center of the merry-go-round is smaller, then when he hops on, it turns out the thing spins with a smaller angular velocity. If he runs straight at the center of the merry-go-round and hops on, he can still hop on at the rim, but if his line of motion intersects with the center of the merry-go-round, the thing won't spin at all. And if he actually lands on the thing at a point below the center, shown in the diagram there, then it'll spin, but in the opposite direction and fairly slowly. So he's got the same momentum in all three pictures. The momentum of the boy is his mass times his velocity. The momentum of the merry-go-round is 0. But the resulting motion after he jumps on is very different in these four cases. And the question is, what's actually different here? And the answer is, it's something we're going to call angular momentum. He's got an angular momentum in the first picture that's larger than the second picture. His angular momentum in the third picture is 0. And we'll see that the angular momentum actually sort of has a sign concept. And the sign of the angular momentum, if you want to think of it that way, is opposite in the bottom picture. Now, the way we're going to define angular momentum, it's actually a vector quantity. But it's a little bit different kind of vector than we've dealt with in the past. In order to understand the vector nature, we've got to develop a concept called a cross product. And the cross product of the boy's angular momentum, the cross product of his r vector and his momentum vector is going to be called the angular momentum vector. The r vector is the vector that goes from the origin of the coordinate system that we're using to compute the angular momentum to the current position of the object, the boy in this case. The momentum vector is the plain old momentum vector we've been using all along. But the cross product is a vector that's actually perpendicular to r and perpendicular to p. And the particular way that we generate that perpendicular vector is the subject of a couple of slides here. But let's suffice it to say for the moment that since v is in the plane of the horizontal plane and r is in the horizontal plane, that you can see that in order to be perpendicular to both of those, the cross product has to be in the vertical direction. So, and it turns out in the first two pictures, the angular momentum points into the page. In the last picture at the bottom, the angular momentum points out of the page. And in the third picture from the top, the angular momentum is actually 0. You can guess, based on the diagram, that probably the angular momentum has something to do with the perpendicular component of the r vector, where the r vector goes from the origin, the center of the merry-go-round, to the boy. So, in fact, it turns out the magnitude of the angular momentum, not the direction, but the magnitude, is the magnitude of the r vector times the magnitude of the p vector times the sine of the angle between the two. And if you look at that a little bit, you'll notice that, in fact, that means that the angular momentum can be thought of as either the perpendicular component of r times the magnitude of p, or it could be the magnitude of r times the perpendicular component of p. Basically, it's the product of the magnitudes of the two vectors times the sine of theta, which gives you a sense in which the two vectors are perpendicular to one another. If the sine of theta is 1, it means they're exactly perpendicular. If the sine of theta is 0, it means they're parallel, which is the opposite of perpendicular, so they're not perpendicular at all, and so that would correspond to the third picture from the top. The r vector points to the left, the p vector, points to the right. Those guys are anti-parallel, which means they are not at all perpendicular, so you get no angular momentum in that picture. Now let's talk a little bit more about how we actually calculate cross products and what it all means. In some textbooks, they don't worry about cross products. They just talk about clockwise and counterclockwise, and that's okay to a point. The problem with clockwise and counterclockwise is that the clockwiseness and counterclockiseness of a rotation depends on your point of view. If you look at counterclockwise from one side of the chalkboard, if you could go around to the back side of the chalkboard and look at the same rotation, it would appear to be clockwise. And similar with clockwise, it looks like counterclockwise from the other side. So that students sitting on opposite sides of a laboratory bench, for example, watching the same object spin, will report that the object is spinning in opposite directions, but it's the same object. It's not really spinning in opposite directions, it's just that their point of view is different. But the cross product is a vector that lives in three-dimensional space, and it has an unambiguous direction, which is the same for any observer, no matter who's looking at the thing. The cross product of A and B in the diagram you see there points toward the observer in the picture. But if there was another observer on the other side, they would see the same cross product, and it would point away from them, but it would be a fixed direction in space. Similar with the clockwise rotation, C and D. So the advantage of a cross product is that it is unambiguous and absolute. Everybody agrees on what it is. And so once you pick a coordinate system, everybody can consistently label a cross product and get the same answer. Okay, so let's think about how we get the labeling right. The idea is, if you point your fingers of your right hand in the direction of the first vector and face your palm toward the direction of the second vector, if you wrap your fingers from the first vector to the second vector, your thumb will point in the direction of the cross product. So you can see that's true if you go back to the first diagram. If you point your fingers in the A direction and wrap them into the B direction, you get a cross product that points out of the board toward the observer in the picture. On the other hand, if you take the fingers of your right hand and point them in the C direction, wrap them into the D direction, your thumb points in a direction away from the observer in the picture. And it can be quite a contortionist exercise to get your thumb and your fingers pointing in the way they're supposed to, based on the diagram in a particular problem. But the good news is it's worth it, because you get an unambiguous result that doesn't depend on how your textbook is oriented or anything else. The other thing is, if something is spinning, it has what's called a spin angular momentum, which is the sum of the orbital angular momenta of all the pieces of the thing about its center of mass. And we can calculate that quite easily using the concept of rotational inertia, which we've already encountered. But we will need to be able to get an angular momentum vector out of that. And the way we'll do it is to wrap our fingers in the direction of rotation, and our thumb will point in the direction of the corresponding angular momentum. That's the idea. And one other thing I should point out before we move on is that it is often necessary in these problems, since they are inherently three-dimensional. The momentum, the r vector, and the angular momentum point in mutually perpendicular directions, and so we cannot avoid three-dimensional notation and three-dimensional diagrams in many problems. And so we need a convenient way to specify vectors that are perpendicular to the plane of the page. And so the convention that we use is that vectors are actually arrows. They have fletching, they have tips. When the fletching is pointing out of the board, that means the arrow points into the board, so into the page vectors, will be denoted by drawing their fletching sticking out, the little feathers sticking out, their X's. If you have vectors pointing out of the board, then the arrowheads are pointing out, and those correspond to little tips. And the dots will be the tips of the arrows pointing out of the board. That's the idea. Okay, let's see how the algebra of this cross product business works. If I define I hat, j hat, and k hat to be unit vectors that point in the x, y, and z directions respectively, you can see that based on our right-hand rule, knowing that the angle between two unit vectors is 90 degrees and their magnitudes are all 1, that I hat cross j hat is a unit vector, perpendicular to each of them, and according to the right-hand rule, you can see that's going to end up being the z direction, or k hat. On the other hand, if you swap the order of j hat and I hat in the cross product, by the right-hand rule, the result is going to point in the opposite direction. So that means that the order of the vectors in a cross product is significant. They're not commutative. You can't just swap the order and get the same answer. In fact, in this case, you can see it turns out to be minus k hat. So then the next thing is you can write out the result of any two unit vectors crossed into each other and see that there are 6 possible combinations. And then you also can see that when you cross them into themselves, you get 0. And so if we take two generic vectors, A and B, and try to compute the cross product, you get a pile of cross terms, but a lot of them are 0, or they reduce to simple unit vectors that point in some other direction. And when the smoke clears, you get the following result. And this result is in the book, and it's on this slide. You should write it down. You can see that you can immediately write down a rule for computing the cross product of any two vectors, given that you have the components of the two vectors. So, and we'll have to do that sometimes. Usually, however, we can look at the picture, use our idea of the right-hand rule, and our understanding that the magnitude of the cross product is the perpendicular component of the first vector times the second times the magnitude of the second, or the perpendicular component of the second vector times the magnitude of the first, or some such thing, in order to compute the cross product. I want to remind you guys of the variables we've been dealing with, like position, velocity, which is the rate of change of position, acceleration, which is the rate of change of velocity, the mass, the momentum, which is the mass times the velocity, the force, for which we have a fundamental principle, the net force is equal to the rate of change of the momentum, and the translational kinetic energy. Now, it turns out in a lot of problems, it's quite easy, or I should say it becomes easy with practice, to identify analogous quantities for rotational motion. So, for example, the analogous quantity of position in rotational motion is the angular position, or the angle. And the rate of change of the angle, of course, is the angular velocity. And the rate of change of the angular velocity is the angular acceleration. Now, there's an analogous quantity to mass. We call it rotational inertia. There's an analogous quantity to momentum, and we call it angular momentum. Now, angular momentum we're learning right now comes in 2 flavors. There's the kind with the boy running at the merry-go-round. That's orbital angular momentum. That's the angular momentum an object has as a consequence of the fact that its center of mass is moving relative to the origin of the coordinate system. But there's also spin angular momentum, which has to do with the idea that an object is spinning about its own center of mass. And spin angular momentum looks just like translational momentum. Algebraically, it's the rotational inertia times the angular velocity. And then notice that looks a lot like mass times velocity, except it's spin angular momentum. There's going to be something called torque, which we haven't got to yet, but we will, and it's sort of a rotational analog of force. It's a twisting force that wants to make something rotate, and the net torque turns out to be equal to the rate of change of the angular momentum, the total angular momentum, which could include orbital and spin components. But notice the similarity with the momentum principle and the angular momentum principle. The torque plays the role of force, the angular momentum plays the role of momentum. Other than that, they're very similar. And finally, we've already encountered this one, but I just want to point it out, that there is rotational kinetic energy, which is 1/2 times the rotational inertia times the angular velocity squared. This is the kinetic energy of the pieces of a system as it spins with an angular velocity omega. It's the kinetic energy they have as a consequence of their motion moving about the center of mass. The translational kinetic energy is the kinetic energy an object has as a consequence of its motion of its center of mass. So that's the idea. So you can see we end up with alphabet soup. For example, one of the problems we dealt with in Chapter 2 were situations involving a constant net force. If we had a constant net force, we could write down an expression for the displacement. So for example, if we have a constant net force in the x direction, and we know the initial x coordinate, and we know the initial x component of velocity, we can simply write down an exact expression for the position of the object in the x direction, the x coordinate of its position, from the momentum principle. We simply integrate a couple of times, and boom, we've got an answer. The cool thing is, if I know I'm experiencing a net torque that's constant, and an object has a fixed axis of rotation, for example, I can simply replace the net force with the net torque, with the mass with the rotational inertia, the initial velocity with the initial angular velocity, and the initial position with the initial angle. And I get an expression for the final angle as a function of time. I don't have to go back and solve the problem all over again because I already know the form of the solution. I just have to know the relationship between the translational and the rotational concepts. That's the idea. Also, just to point out that the rate of change in momentum is equal to the net force looks a lot like the rate of change of the angular momentum equals the net torque. So the momentum principle and the angular momentum principle are really strongly related by this correspondence between translational quantities and their rotational analogs. Finally, the total kinetic energy of a system is going to be the sum of its translational kinetic energy, its rotational kinetic energy, and its vibrational kinetic energy. And we haven't talked a lot about vibrational kinetic energy, but you can imagine that that has something to do with the radial component of the velocity of the pieces of the system, whereas the rotational kinetic energy has to do with the angular velocity of the pieces in the system. So that's kind of how it works out. Very good. Let's talk about torque. Torque is just a force that tends to make something want to change its angular momentum. So let's say I have a random object acted on by some force, and I want to compute the torque. The answer is I find the angle between the force and the location where the force is applied. Sometimes that's called, there's a concept called moment arm, which is the perpendicular distance between the line of force and the axis of rotation. But it all comes out of this cross product between the r vector and the f vector. The r vector goes from the axis of rotation to the point of application of the force. The f vector is just the force vector, and the torque is the cross product of the two. And as usual, you can either take the perpendicular component of r, which is sometimes called the moment arm, times the force, or you can take the perpendicular component of the force times r. Either way, you get the same answer. Now, what is the rate of change of the angular momentum? It's the rate of change of the torque. I'm saying that wrong. The rate of change of the angular momentum is the rate of change of r cross p by dt. This is in a case where we're talking about orbital angular momentum. Well, using the product rule, that's dr dt cross p plus r cross dp dt. Now, I want to point out that dr dt is velocity, and velocity and momentum are always in the same direction. So dr dt cross p is 0. So that means that the rate of change of the angular momentum is really just r cross dp dt, but we already know dp dt is f, so the rate of change of angular momentum is r cross f, and that's the torque. So that's a limited form of a derivation of the angular momentum principle, assuming that the angular momentum is orbital angular momentum. Okay, let's see if we can figure out the spin angular momentum based on our understanding of orbital angular momentum. The spin angular momentum is the orbital angular momentum an object has. I should say it's the sum of the orbital angular momenta all the pieces of an object have relative to their motion about its center of mass. So let's say we have an object that's spinning with some angular velocity, omega. And let's look at a particular piece of it. We know that the velocity of a piece is omega cross r, but let's actually show that. The point is, omega is a vector that points out of the page. That's why omega is a dot. The r vector for a particular piece, it goes from the center of mass to the piece, and so omega cross r has the right direction, because if you point your fingers out of the page and wrap them into the r vector, you get a vector that points in the direction of motion of the object. So the idea is that the direction of the velocity is certainly correct for omega cross r. What about the magnitude? Well, the magnitude is going to be the magnitude of omega times the magnitude of r times the cross product of omega hat and r hat. Well, omega hat and r hat clearly have the correct direction for the cross product, but is omega times r the correct magnitude? And you can see that it is. It's the circumference of a circle of radius r divided by the period of one orbit. So I think everything's okay. The angular momentum, of course, is r cross p. But p is m times v, so you put m times omega cross r, and you end up with this thing m times r cross omega cross r. But if you think about that for a little bit, you'll see that that's mr squared times omega. Omega cross r points in the v direction, r cross v points back in the omega direction, so you end up with mr squared times omega all over again. So a single point has an angular momentum that is mr squared times its angular velocity vector. Notice that we already worked out back in, what, chapter 8 or something, chapter 7, I don't remember now, that the rotational inertia of a point mass is mr squared. So this is just I times omega. That's our old friend. And that's true of each of the point masses in the system. So that means that the total angular momentum is the sum of the mr squareds times omega. And of course, that harkens back to our definition of rotational inertia. And so we define rotational inertia to be the sum of the mr squareds. That's kind of the idea. So the angular momentum for the spin angular momentum is the rotational inertia times the angular velocity. The rotational inertia is nothing other than the sum of the mr squareds. Now, we already worked this out for kinetic energy, but it works out the same way. If you go to calculate the kinetic energy, it turns out the omegas factor out. The half factors out, and you get this sum of mr squared again. And so the rotational kinetic energy, that associated with the rotation of an object about its center of mass, is 1/2 I omega squared. And I is nothing other than the exact same thing we found before. It's the sum of the mr squareds, or it's the integral of r squared dm. So let's take some examples. If we have a ring where all the mass is at the same radius, or a point mass at a particular r, then the rotational inertia is just going to be mr squared. If we have a rod that's spinning about one end of the rod, say, and we want to know the rotational inertia relative to that axis of rotation, we simply compute dm r squared. Of course, dm is the total mass divided by the total length times dx, and we put that in and we get 1/3 ml squared. You can do the same thing with a uniform disk, which we already worked out in class, but there it is again. Or you could do a sphere, which we haven't worked out, but it's entertaining to do so. You can try it out sometime. So what we like to do is to divide the translational and rotational angular momentum into, or the total angular momentum into pieces, translational and rotational. And the total angular momentum is, of course, the sum of the two. And you can see that that's equal to the total torque acting on the system. So when you plug all that in together, you can see that the rate of change of the translational angular momentum turns out to be the torque on the center of mass due to the net force, and that the rate of change of the rotational angular momentum is the sum of the torques taken about the center of mass. So we'll see how that works in some of the problems. And finally, the last piece is that in a microscopic system, angular momentum is actually quantized. It can only take on certain definite values. So for example, if you think back to the Bohr model we discussed in Chapter 8, the angular momentum turns out to be an integer multiple of h bar. I should say the z component turns out to be an integer multiple of h bar. This is essentially equivalent to the conjecture that the de Broglie wavelength has to fit around an orbit an integer number of times. If you play with this a little bit, you'll see that it turns out to be exactly the same condition. And as we did in class for our group problem-solving exercise, you can show that this implies that the orbital radii are quantized, have definite orbital radii, and that orbital radius turns out to be proportional to this n, the same n that quantizes the angular momentum. It gets squared in computing the radius of the nth orbit, and the energies are correspondingly quantized, and if you plug all that in, you'll see that the energies turn out to go like 1 over n squared. And these results are familiar to you from Chapter 8, but not until now have we defined what angular momentum is so that we could even talk about where they come from, but that's basically the story. The other thing is that in a modern view of the orbit of electrons, there are no actual circular orbits. Basically what you end up with are probability density clouds of various shapes and sizes. And you can even compute under different circumstances the probability or the rate at which probability transitions from one state to another. But the angular momentum and the energy are quantized in exactly the same way, even in the modern view. The z component of momentum turns out to be an integer multiple of h bar, and the total angular momentum turns out to depend on L times L plus 1, where L is an integer or a half integer. So, for example, if you're talking about orbital angular momentum, L would be an integer, but the spin angular momentum of a particle turns out to be half integer for most matter particles like protons and electrons and things like that, neutrons. So it gets quite interesting, but I just wanted to point out that this angular momentum concept works all the way down to the microscopic scale, with the minor change that it turns out it gets quantized at that point. So that's the end. We'll see you guys next time.